Good friend of mine, Paolo Piccione, is your name, right? And today he's going to talk about function with critical points in pairs. It's too long, the title. In pairs and orthogonal geodesic chord. Thank you, Paolo.
Thank you, Jose, for inviting me. I hope you don't regret afterwards. My goal today is to keep you awake for 40 minutes.
That's complicated.
With some easy stuff. I know this is a particularly hard task after the several caipirinhas that most of you drank last night, but I will still try to do my best. Okay, the talk is divided into three parts, and in the first part I will talk a little bit about topology. In the second part I will speak a little bit about analysis and some ODEs, and in the third part, finally, I will speak about geometry. So let me start with the first part, and I'll take a ride with some of the definitions that Graham gave in his talk. So I will speak about a little bit about Morse theory. So I have my favorite compact manifold, which is a sphere. I have a smooth map on the sphere, and I want to count its critical points, okay? So I want to use Morse theory. But the topology of the sphere doesn't help very much because Morse theory only tells me that this function must have at least two critical points, one minimum and one maximum. And big deal, I mean, every compact manifold has that property, right? And in fact, Reeves' theorem says that if you have a compact manifold that admits a smooth function having only two critical points, then it must be the sphere. So this is really the worst object you can think of if you want to find many critical points, okay? Things get a little better if you assume that F has some symmetry. For instance, if F satisfies the f of x is equal to f of minus x, that is, it's an even function, then you can define, using this f, you can define a function on the projective space, right? So this gives you an induced map on the projective space RPN. And smooth functions on RPN have a lot more critical points. They have at least n plus 1 critical points. So this function here must have at least n plus 1 critical points if it satisfies something of this type, okay? So I want to use this fact to prove a similar result in a slightly more general case, which is what I call the case of even Morse function. Even Morse function. Morse even functions. So let me tell you what a Morse even function is. Suppose that M is a compact manifold. Okay, you call beta k the kth Betti number of the manifold. Okay, this is the kth Betti number. Of M. And suppose now you take a smooth function of M. You call mu k the number of critical points of F having Morse index exactly equal to k. I think this has had a different name in Graham's talk. So this is the number of critical points of F having Morse index equal to k, okay? Now F, I say that F is Morse even if these numbers here are always even, okay? If mu k is an even integer for all k, going from 0 to the dimension of m, okay? So that means if you have a way of classifying critical points in pairs, exactly like in the case of even functions. If you have an even function and it has one critical point, then also its antipode is evidently a critical point, okay? So Even functions are examples of Morse even functions. But evidently, this notion is more general than this case here, okay? The first result, oh, by the way, I will try to make complete proofs in this talk. So, the proposition is that if you have a Morse even function on the sphere, then you have exactly the same critical points as even functions. That is, then f has critical points of arbitrary Morse index. K, say, from 0 to m, the dimension of the manifold, okay? That means beta k, oops, I'm sorry, mu k is different from 0 for all k. Okay, so you, in particular, you have at least k plus 1 distinct critical points. Proof. So you have, Morse theory gives you an inequality between these numbers. The inequality is slightly better than the inequality that Graham gave. You have something like mu 0 is greater than or equal to beta 0. Mu 1 minus mu 0 is greater than or equal to beta 1 minus beta 0. And then mu 2 minus mu 1 plus mu 0 is greater than or equal than beta 2 minus beta 1 plus beta 0, and so on, okay? So we know the betas for the sphere. Beta 0 is 1, beta m is 1, all the other ones are 0, okay? So the first inequality tells you that mu 0 has to be greater than or equal to 1. But we know it's an even number, so mu 0 has to be greater than or equal to 2, okay? And then from this you get that mu 1 is greater than or equal than mu 0 plus beta 1 minus beta 0. So you have this is greater than or equal to 2 plus 0 minus 1. That's 1. Right? And so this is an even number, so in fact it must be greater than or equal to 2, and then you keep doing this and you prove this. Okay? Very good. So you have this type of results holds also for manifolds that are not necessarily the sphere. What you really need is that all the Betti numbers of the manifold you want to consider have to be even numbers, except for the first and the last one, okay? So in general, if you have a manifold which has all its Betti numbers even, then a Morse even function on such a manifold has mu k, which is not only greater than or equal than beta k, it's actually strictly larger than beta k for all k, okay? How many manifolds do we know that satisfy this condition here? In dimension 2, if you take M, a compact manifold of dimension 2, every orientable surface satisfies this condition, because an orientable surface of genus G has beta 1, which is equal to 2 minus 2G, which is an even number. So in dimension 2, this theorem is very good. In dimension 3, you have, okay, in dimension 3 you have that beta 1 is equal to beta 2, right? Right, yes. So if you take simply connected manifolds, beta 1 is equal to 0, beta 2 is 0. and you only have the sphere, 3 spheres. So in dimension 3, there's not much you can say. But in dimension 4, there's a lot of manifolds that satisfy this assumption here, because in dimension 4, what happens so suppose you take a compact manifold, orientable compact manifold of dimension 4, say simply connected. Then you have beta 0 and beta 4, of course, are equal to 1. Beta 1 and beta 3 are equal to 0, so you only look at beta 2, right? And beta 2 in dimension 4 is additive by connected sums, right? So you can make connected sums of CP2. Remember that beta 2 of CP2 is equal to 1, and beta 2, and then there's another model which is S2 times S2, and this is equal to 2, okay? So if you make a connected sum of any number of S2 times S2 and an even number of CP2s, then you have manifolds that satisfy this condition here, okay? This is all I wanted to say about topology. Easy enough, right? Okay. Now, let's change topic. If for some reason you miss something in the first part, don't panic. This part will be independent of the first one. So now let's consider a Riemannian manifold which represents the configuration space of some physical system. And let's take a potential which is a smooth function on M. And then we look at the equation second derivative of x equals minus the gradient of v. X is a curve in M. So solutions of these equations represent trajectories of a conservative Lagrangian system. And as everybody knows, there is a constant associated to each solution of this equation, which is the energy. There is a number E constant, which is equal to kinetic energy plus potential energy of any solution, okay? And it is an interesting, where do these solutions, if you fix a value of E, then solutions of these equations satisfying this conservation law, they live in a set which I will call omega E, which is the sublevel of the function V corresponding to the value E. Okay, they must live inside this set here. And what people want to do is they want to count periodic solutions of this equation with a fixed value of the energy. Okay, so that means that we have to compute periodic solutions of this equation living here. Okay, so something like curves here. But there's another type of periodic solutions that are solutions of these equations whose final and end, whose initial and final endpoint are on the boundary of this object, which is exactly where the potential energy is equal to E, so that this has to be 0, which means that this is like a pendulum solution. It goes, the particle goes all the way up to this point, which has a maximum potential energy, and then it goes back, so it's like a pendulum-like periodic solutions, okay? This type of periodic orbits are called break orbits. Okay? And it is a particularly interesting question to ask is, how many break orbits does a potential system, a conservative system like this have, okay? And there's a very famous conjecture by Seifert, 1947, that says that if omega E is homeomorphic to an M ball, an M plus 1 ball, if this is homeomorphic to a ball of dimension, let me say, M plus 1, then there must be at least exactly M plus 1 break orbits of energy E. This is a very famous conjecture. It has been proved in some cases, but the general case is still an open problem. And this is the type of question that I would like to ask myself, okay? So I want to count break orbits of some conservative system like that. Okay, as you know, there is a variational principle which says that solutions of this equation with fixed energy are geodesics in a conformal metric, which is called the Maupertuis metric, okay? And this metric looks like this. So it's a metric conformal to the original metric G, but you have to multiply by E minus the potential function. Geodesics in this metric here correspond to, up to parameterization, correspond to solutions of this equation satisfying this. Okay? Maupertuis principle, this is from the 19th century. So basically, I want to study geodesics in this, with respect to this metric, in this manifold which is homeomorphic to a ball. But look at the problem, is that on the boundary of this ball, the metric degenerates, because this factor is 0 on the boundary, okay? So basically, I want to study this geodesics in a singular metric on the boundary, okay? And the first result is the following, is that if you assume that E is a regular value for the potential function, so that in fact the boundary is a nice, smooth hypersurface, then you can do the following trick. So you have, this is the singular boundary. You can remove a small neighborhood of the boundary. You have this omega E is the large one, and inside you have a smaller domain, omega prime, which is still homeomorphic to a ball. Okay? It has smooth boundary. And now the geodesics in omega prime that arrive orthogonally onto the boundary of this new object, they can be uniquely extended to geodesics in the original singular ball. Okay? So if you remove this part, you're left with a nice, regular, orthogonal geodesic problem. Okay? So with this, let's say our Seifert conjecture will be proved if we prove that if you have a Riemannian manifold which is homeomorphic to a ball, then it has at least M plus 1 orthogonal geodesics to the boundary, okay? Which in this generality is false. You can give examples of balls that admit no orthogonal geodesic at all, okay? So we must use some special property here. Usually, balls that have lots of geodesics orthogonal to the boundary are when the boundary is convex, okay? Then you can do this minimax arguments, okay? But for that, you need convexity of the boundary, because when you shorten a curve, you make it shorter, you take geodesic, and you have to make sure that the geodesic remains inside your boundary, okay? So if you have a convex boundary, then the problem is easy. And how about the break orbit problem? Does it give you a convex boundary? No. It gives you exactly the opposite. It gives you a concave boundary. It gives you a concave boundary, strictly concave. So you cannot use minimax arguments, okay? And so this concludes the second part of the talk. And now I go to the third part where I will discuss the problem of how to find a good number of orthogonal geodesic chords in Riemannian balls, okay? So now I take a manifold, which let me call it omega, okay, which is homeomorphic to an m+1 ball. And it has a Riemannian metric, no singularity now. I have removed the singularities, okay? And I want to count what I call orthogonal geodesic chords, okay? OGCs, that means geodesics that start orthogonally and arrive orthogonally, okay? And the class of examples that I want to study is of the following type. I assume that my metric G will have this property, okay? I will write this down in a second. Let me first say what this is about. I want to assume that if I start from a point on the boundary, I take the unit normal vector pointing inside, I shoot the orthogonal geodesic, then this geodesic at some point arrives on the boundary transversally. This is the assumption that I want to make. Is this clear? So from every point, I start with the orthogonal geodesic, and I want to assume that this geodesic at some point will exit transversally from my ball. This is the assumption 1. Maybe I could avoid writing it. It would take me 5 minutes. It's easier to say it this way. So is this assumption clear? So you see, I'm trying to avoid two situations. One situation is that I want to avoid that an orthogonal geodesic at some point is tangent to the boundary. Okay? This is a case that I want to avoid. And the second case that I want to avoid is the case where there is some geodesic, there's some orthogonal geodesic which, when shot inside, then it remains inside forever. I want to avoid that. Okay? Does this have to do with convexity of the boundary? No, no. It has to do with changing the type of convexity of the boundary. Okay? You can have concave things like the ones occurring in the break orbit problem that satisfy this. For instance, if you take a sphere, remove a small convex disk, then the remaining part has concave boundary. But it has this property. You see, you can shoot a geodesic and arrive orthogonally onto, and arrive transversely onto the other side. So this assumption here does not have to do exactly with concavity or convexity of the boundary, okay? Actually, I should write this down. So there exists, this assumption 1 says that there exists a function, let me call S, depending on the metric G, which is defined on the boundary of omega, and taking values in the set of positive numbers, such that for all p in the boundary, if I take the geodesic gamma p, which is the geodesic starting at p orthogonally to the boundary, and I compute this at the time Sg of p, this again belongs to the boundary, and it's transversal. And gamma p prime at the point Sg of p must be transversal to the boundary. Okay? Very good. The transversality assumption tells me immediately that this function has to be smooth. This function S, which is like a crossing time function, okay? This function has to be smooth by transversality, okay? So SG from the boundary of omega to 0 plus infinity is smooth. Okay? Now I have a question for you. Guess what the critical points of this function are. I know what you're thinking of. I anticipate your answer, and it is P is a critical point if and only if the geodesic gamma P arrives orthogonally also. That's almost true, but not quite. Let me tell you what could go wrong. Suppose, let me give you this example. Suppose that the boundary has a circular portion, okay? So this is the center of this circle. And suppose that another piece of the boundary passes here. So you have something of this type. In the plane, this is an example in the plane. It's a two-dimensional example in the plane. Okay? So you see that this crossing time function is constant here, right? So these are all critical points of this function, but none of these geodesics arrive orthogonally. None of them. Okay? So this happens precisely when this point here, which belongs to the boundary, is focal to the boundary. Is focal to the boundary. So the assumption 2 that I want to make is that the boundary should not contain any point which are focal to the boundary. The assumption 2 that the boundary of omega does not contain boundary omega focal points How bad is this assumption? Some of you may think that this is generic. It is not. I will show you an example where this is not satisfied in a specific case and also in perturbations of this case, okay? But you will agree with me that this is an open condition in the C2 topology. This is an open condition in the C2 topology, okay? By the way, A1 is an open condition in the C1 topology, okay? This is an open condition in the C2 topology, and they are both satisfied in some particularly nice example. For instance, if you have something which is rotationally symmetric, then it will satisfy both examples here. So in particular, my theory will apply to an open set of metrics that contains the rotationally symmetric ones, okay? I will give you an example in a minute to show you that that condition is not generic, although usually one usually thinks that the existence of focal points in a sense is something which shouldn't happen too often, okay? Okay, under this assumption here, then the critical points of this function are orthogonal geodesics, okay? Very good. Now, this is a function which is defined on a sphere of dimension m, and I want to look for its critical points, right? Now, the next step is I want to show you that this is a Morse-even function. Now, you have to remember what I said at the beginning of my talk. You have to consider Morse-even functions on spheres, okay? Now, I want to show you that this is a Morse-even function. How am I going with time? 11:20. 11:20. Very good. Okay, so remember what is a Morse-even function means that associated to one critical point, I should have another one with the same Morse index. Okay? So, what do you guess? I have my ball. I have a critical point. So that means that this geodesic starting orthogonally here at some point arrives orthogonally here. So P is a critical point. Which is the other critical point associated to P? clearly this one here. This one here, right? This is the point gamma p of SG of P. This is a different critical point. It can't be the same. This geodesic cannot have come back to the same place by uniqueness because they're both orthogonal. This can't happen. So this point is certainly different from this one here, okay? So the critical points are an even number. The important thing is to show that the Morse index of the function SG at the point P has to be the same as the Morse index here, okay? Let's see how we prove that. This geodesic gamma p, this is obtained as a critical point of the function SG, but there is also like an infinite dimensional problem for geodesics with both endpoints on submanifolds, right? This is an infinite dimensional problem. You take all possible paths starting on the boundary and terminating on the boundary. You take the length functional or the energy functional, and you take the critical points of this object. So you have an infinite dimensional variational problem associated to that, okay? And the geodesic gamma p has a Morse index as a critical point of this infinite dimensional problem, okay? So there is a Morse index. There's two notions of Morse index here. There's Morse index of the function SG, and there's a Morse index as the variational problem of free endpoint geodesics, okay? And these two objects are related, okay? And what relates these two things is the Morse index theorem for free endpoints geodesics, which is something not very known usually. Everybody knows the Morse index for fixed endpoints geodesics, right? Morse index is equal to the number of conjugate points. Then you have a version for focal points. If you take a geodesic which starts orthogonally from a hypersurface, say, and terminates at one point, then the Morse index of this object is equal to the number of focal points, okay? And there is also another version of this theorem that tells you how to compute the Morse index of geodesics in general that have both endpoints orthogonal to submanifolds, okay? This is not so known, this theorem, but basically what it says is that the Morse index of the geodesics gamma p as an infinite dimensional variational problem. This is computed as the number of focal points of along gamma p, that is so you start from P, you consider focal points corresponding to this first initial submanifold, plus the Morse index of SG at the point P. You see what this theorem is saying? So two things. This part takes care of the contribution of the first initial submanifold. And the second part is the contribution of the final submanifold, okay? This is a highly non-symmetric object, okay? I don't know if you ever thought about it, but if you take like a fixed point Riemannian geodesic, you take an initial point and a final point, okay? The number of points that are conjugate to the initial point is the same as the number of conjugate points or points that are conjugate to the final point. There is no easy way to see this unless you use the Morse index theorem, because you know that the number of these points is equal to the Morse index of the object, right? But otherwise, there is no obvious relation why this should be true, okay? But it is true. Now, look at this expression here. Evidently, the left-hand side of this equality does not depend on the orientation of gamma, okay? But both terms on the right side do depend on the orientation of gamma. So this is also equal to the number of focal points along not gamma p, but the gamma p run in the backward with a backward orientation, plus the Morse index of SG, not at P, but at the other point, at this point here, at Q, right? So remember that I want to show that this is equal to this, right? And the equality that I want, that is this second term is equal to this, would be true only if the focal points along gamma p run in one direction or the other direction would be the same, right? And how do I know that? Is it true that if you have an orthogonal geodesics to the boundary, then the number of focal points must be the same? No, in general, this is not true. Let me give you an example. Suppose this is a two-dimensional example. So suppose you take here a piece of straight line, and then you connect it, and then here you take an arc of a circle, okay? So that this geodesic here arrives orthogonally. If you run this geodesic in this direction, there is no focal point, because this is flat, right? So if you run in this direction, you get no focal points. On the other hand, if you start from here, when you arrive to the center of the circle, you have one focal point, right? So in general, it is not true that this object is equal to this. But in our special case, we can avoid this situation. Why is that? Suppose that this is the case. Suppose that we have one geodesic which has some focal points going in one direction and no focal point in the other direction, okay? And let's do the following game. Let's take this geodesic and let's move it by maintaining the first initial point orthogonal here, okay? Until it arrives at this point here. You see, we move it orthogonally to the boundary. We don't worry what happens to the other endpoint. Okay? Okay, there was a focal point at this initial position, but there is no focal point at the final position. Where has this focal point gone? It can't have disappeared. Focal points do not disappear. Okay? What they can do is they can either collapse on the boundary or go outside, right? They cannot collapse to the boundary by compactness. Focal points must be far from the boundary, from the initial submanifold. Uniform, you can make this uniform along the entire thing. So this focal point cannot have collapsed on the boundary. It must have gone out. It must have gone out. But if it went out at some point, it must have gone through the boundary. And that's impossible because our assumption A2 says that there are no focal points on the boundary. That cannot have happened. So this situation does not happen. So it is true that the number of focal points in the two directions is the same. So it is true that these two Morse indices are the same. So it is true that SG is a Morse even function on a sphere, on an m-dimensional sphere. So it must have exactly m plus 1 critical points, which is exactly the number of break orbits given in Seifert's conjecture, okay? So conclusion, Seifert's conjecture is true for a C2 open subsets of potentials. that contain, say, the rotationally symmetric one, okay? Let me just finish with one observation. This very example shows you that the assumption A2, that is, there are no focal points on the boundary, is not generic. Because evidently this situation, one focal point in this direction, no focal points in this other direction, has to be maintained also by small perturbations of this object. So this assumption is not generic, okay? Thank you very much for your attention.